Right now, somewhere in a server farm you've never heard of, a machine is copying your encrypted data. Not hacking it, not breaking it, just storing it, waiting, your bank records, your medical history. Every private message you've ever sent through a secure app. Someone, somewhere, is betting that in a few years, a machine will exist that can crack it all open, and they want to be first in line when that happens. This isn't a conspiracy theory. It's a real name strategy that intelligence agencies and cybersecurity firms openly call harvest now, decrypt later. And in the last 18 months, the machine they're waiting for got a lot closer to being real. Not science fiction close, not maybe in 50 years close. Close enough that the United States government has already set a legal deadline for it. Close enough that Google, IBM, and NVIDIA have all quietly redesigned what a data center is supposed to look like. This video is about what actually happened, what it actually means, and why the answer is a lot stranger and a lot more interesting than the headlines are telling you. Let's start with what actually broke through, because most people get this part wrong. In December 2024, Google's quantum computing division unveiled a chip called Willow, 105 qubits, built in a custom fabrication lab in Santa Barbara. Now, quantum computers had been getting bigger for years. That's not the news. The news is what happened when Willow got bigger. In every previous generation of quantum hardware, adding more qubits meant adding more errors. Quantum information is incredibly fragile. A stray vibration, a tiny bit of heat, a cosmic ray passing through the chip, any of it can corrupt a calculation. So historically, bigger quantum computers were noisier quantum computers. That's the wall the entire field had been stuck behind for almost 30 years. Willow broke that wall. Google's team grouped physical qubits into larger and larger clusters. They call this a surface code. And each time they scaled the cluster up, the error rate went down. Not up, down. In the published results, later verified in the journal Nature, each increase in cluster size cut the logical error rate roughly in half. Researchers call this below threshold performance. And it's the thing the entire quantum computing industry has been chasing since the 1990s. Think of it like proofreading a document. If you have one proofreader, they catch some mistakes and miss others. If you add 9 more proofreaders and they all have to independently agree before a correction sticks, you'd expect errors to get rarer as the team grows, but only if the proofreaders are actually competent. For decades, quantum proofreaders weren't good enough. Adding more of them just added more chaos. Willow was the first real proof that above a certain quality threshold, adding more actually does make the system exponentially more reliable. That's a genuinely big deal. But here's where I need to slow down, because this is exactly the point where most videos on this topic start exaggerating. Willow did not crack your bank's encryption. It didn't break the internet. What it proved is that the engineering path to a large, reliable quantum computer is real. Not guaranteed, but real. And that single proof is enough to change how governments and corporations plan for the future. Because once you accept that a machine capable of breaking modern encryption is plausible on a 10 to 15 year horizon instead of maybe never, everything downstream of that assumption has to change today. And that's where the story gets a lot more concrete and a lot more urgent than a lab chip in California. Here's the thing. Almost nobody explains properly. The danger was never about tomorrow. It's about what happened years ago. Nearly all of the encryption protecting the modern internet, your bank's website, your email provider, your company's internal servers, relies on math problems that are extremely hard for a normal computer to solve. But that a sufficiently powerful quantum computer could solve using an algorithm mathematicians have understood since 1994, called Shor's algorithm. The reason Harvest Now Decrypt Later works as a strategy is simple. Encrypted data doesn't expire. If someone steals a copy of your encrypted files today, that copy just sits there. It doesn't matter that today's computers can't crack it. The attacker isn't trying to break in today. They're archiving it and waiting for the lock to become obsolete. This is exactly why the U.S. National Institute of Standards and Technology, NIST, spent years finalizing a new generation of encryption standards designed to resist quantum attacks, officially published in 2024 under the names FIPS 203, 204, and 205. And this isn't just an academic recommendation anymore. The U.S. government has set an actual compliance deadline. Federal agencies and contractors are required to phase out today's standard encryption algorithms by 2030, with a complete ban on them for sensitive systems by 2035. The National Security Agency's parallel guidance for national security systems follows a similar 2030 to 2035 timeline. Australia's Cybersecurity Agency has recommended an even more aggressive cutoff. Europe is pushing hybrid encryption now, with full adoption targeted by 2035 as well. And this is the part where honesty matters, because a lot of channels will tell you a quantum computer capable of doing this exists right now or will exist next year. It doesn't, and experts don't agree on exactly when it will. Some analysts have floated 2028 as an aggressive early estimate. Security planning firms and boardroom risk assessments tend to center on a window between 2029 and 2035. Nobody serious is claiming certainty here. This is genuinely disputed among people who study it for a living. But here's the detail that should actually worry you more than any single prediction. Because of harvest now decrypt later, the deadline that matters isn't when the quantum computer arrives. It's when your data stop being safe to steal, which, if you've sent anything sensitive over the internet in the last few years, may already be in the past. Boston Consulting Group has put it bluntly in their industry guidance. Organizations that wait until 2030 to start migrating will already be too late. So encryption is one half of this story, and it's the half almost every article on this topic stops at. But it's not the half that made this title true. Because while cryptographers were racing to rewrite the internet's locks, a completely different kind of change was happening inside the buildings that run the internet itself. And this part, almost nobody's talking about yet. For 70 years, a data center has meant one thing: rows and rows of classical silicon chips, CPUs, and more recently GPUs, sitting in racks, cooled by air or liquid, running on binary logic. Every data center built today, from a small regional facility to a hyperscale AI campus, is built entirely around that one assumption. That's about to stop being true. At NVIDIA's GTC conference in 2026, the company introduced something called NVQLink, an open architecture specifically designed to plug quantum processors directly into the same racks as NVIDIA's GPU supercomputers, using real-time software connections fast enough to handle live quantum error correction. NVIDIA's CEO, Jensen Huang, said, "The company expects every NVIDIA GPU scientific supercomputer in the near future to be hybrid, tightly coupled with quantum processors as standard equipment, not an experimental add-on. This isn't a hypothetical roadmap slide. It's already being built." In February 2026, a company called SDT opened South Korea's first commercial quantum AI hybrid data center in Seoul, physically combining a 20-qubit superconducting quantum processor with NVIDIA's DGX systems in the same operational facility, one system handling heavy numerical work, the other handling quantum-specific calculations, passing work back and forth in real time. The U.S. Department of Energy's Oak Ridge National Laboratory installed a similar hybrid system in early 2026, right alongside Frontier, one of the world's fastest existing supercomputers. Pacific Northwest National Laboratory is building an open-source version of the same bridge using NVIDIA's hardware. And in July 2026, a Shanghai-based startup called Zhongqi Wuliang unveiled something even more direct: a quantum computer built into a standard server chassis, sized and shaped to slide into an ordinary data center rack alongside conventional equipment rather than requiring its own dedicated lab environment. Do you see the pattern forming here? None of these projects are about replacing classical computers. They're about adding a third type of resource into the same physical building, one that speaks a completely different electrical and logical language, needs different cooling, different control systems, different physical space, and that's the actual literal sense in which a facility built today starts to look outdated. Not because its GPUs stopped working, but because it was never designed with room, power delivery, or interconnects for the thing sitting next to them tomorrow. But before you assume every data center on Earth needs to be torn down and rebuilt, I want to give you the other side of this, because the balanced picture is actually more interesting than the scary one, and it's the part almost every other video on this topic skips entirely. First, quantum computers, even the best ones today, are still what researchers call NISQ devices: noisy, intermediate scale, and nowhere close to running most everyday business software. IBM's newest chip, Nighthawk, has around 120 qubits and is targeting practical quantum advantage by the end of 2026. Targeting it, not guaranteeing it. Google's own public roadmap places its next major hardware milestone, a large-scale error-corrected machine, somewhere near the end of this decade. And Google's leadership has said publicly that they're tracking closely to a roadmap they laid out back in 2020, not accelerating wildly beyond it. These are serious, credible companies being unusually careful with their own predictions, which is itself a signal worth paying attention to. Second, and this is the twist a lot of quantum hype content completely ignores, some of the most impressive computing breakthroughs of the last year didn't come from quantum hardware at all. In early 2026, a company called OTI Lumionics used ordinary NVIDIA GPUs to simulate complex chemistry problems using quantum-inspired mathematical methods, and reported a 90-times speedup, cutting simulations that used to take days down to about an hour. That's not a quantum computer. That's classical infrastructure, the exact kind sitting in data centers right now, getting dramatically better at mimicking quantum-style calculations without needing an actual quantum chip at all. It's a reminder that quantum and obsolete classical computing are not the same story. In many cases, they're pushing each other forward together. So where does that leave the actual honest answer to this video's title? Here it is, without the exaggeration. Today's data centers are not becoming worthless. Your existing cloud provider isn't shutting down next year. But two very real, very current shifts are already underway. And both are things a facility built today, with today's assumptions, simply wasn't designed to handle. The first is cryptographic. The security model protecting nearly everything stored in modern infrastructure has an expiration date that regulators have already written into law, and the clock started ticking the moment that data was first captured, not the moment a quantum computer actually arrives. The second is physical. The newest generation of computing facilities are being built from the ground up to host a resource that doesn't exist in a single server rack today. A live, low-latency bridge between classical processors and quantum ones, something companies like NVIDIA, IBM, and a growing list of national labs and startups across the US. Now, South Korea and China are treating not as an experiment, but as the next standard architecture. If you found this genuinely useful, A-like helps this channel reach more people who are trying to understand what's actually happening in tech, instead of just reacting to scary headlines. And if you want more breakdowns like this one, subscribing means you won't miss them. Here's the honest way to think about all of this. Every major computing shift in history didn't announce itself with a single dramatic moment. Mainframes didn't vanish the day personal computers appeared. The cloud didn't erase physical servers overnight. What actually happens is quieter and slower. The assumptions engineers build on top of start shifting, one deadline, one lab result, one new rack architecture at a time. And by the time most people notice, the foundation has already moved. That's what's happening right now, in real facilities, on real government timelines, funded by real budgets. Not a single dramatic breakthrough that changes everything overnight, but a set of deadlines and decisions being made this year that will quietly decide who's ready for the next decade of computing and who spent it catching up. If this kind of story is the kind of thing you want to keep understanding as it unfolds, subscribe, and I'll keep bringing you the real version, not the exaggerated one.